Actually, in order to prepare for this, I've watched multiple keynote speeches, Ramsey's, for example, Ann's from last year, Andy's from the year before. And all of them mentioned there is some bright, blaring lights coming out. Those are the two lights. I couldn't believe it's actually that bad. But like any good AI model, I watched their talks and I learned a few things. And what I learned from those is that they actually told a personal story as well as a technical story. So I'm going to try to kind of weave in a little bit of my own personal journey, because my understanding is that this conference is about half or 50% students and 50% professionals. And I think my personal story might be inspiring to some of the students, because I've come through the same routes that most of you are going through. So let's get started here. If you have a burning question, please raise your hand. You can ask me. I would rather this be kind of an interactive session rather than a boring one. But if you have a long question, we can take it offline. I'm here today and tomorrow. I'm feeling a little bit under the weather, so that's why my speech is a little bit muffled. But other than that, I'm perfectly healthy and happy to engage with you. So I also want to thank the organizers as well as the USENIX team, Heidi and team, and more importantly, all of you for giving an hour of your time. I take this very seriously, and I hope you'll get something out of my presentation. So I organized my presentation into mainly 3 parts. I'll spend a little bit of time on my own personal journey in how I've come to where I am right now. The second part of it is mostly the technical part, which is what's really new in AI. And I've actually used a lot of AI to even come up with the presentation here. So that'll be interesting. We'll talk about a little bit of the AI workloads, because when I look at the past keynote speakers and the speakers that in general here, they're all storage experts. And I'm not a storage expert. So as I was thinking back, what is it that I can tell you guys that's actually new to you? And what is new really now is a new workload. Obviously, storage guys gets excited by the new workloads. So AI is the new workload. And I want to talk about what are the systems that we are building for AI, what are the kinds of challenges we are seeing, compute network storage-wise. And so I'll spend some portion of this talk at the end on the storage parts of it. But I also want to connect the compute and the network aspects of challenges in AI systems. And finally, I'll do a brief summary of it. Okay? All right. So I'll make this really short, just as an inspiration. I'm not going to rehash everything that happened in my whole life. But I actually started my career at IBM Research while I was doing my graduate program. I think it was in second year or third year. I got an internship at IBM T.J. Watson Research Center. And I've never left. I love that place. It's a great environment. And if you find something like that, definitely hold on to it. But the first 7-8 years of my career is probably the time where I did the most intense technical work. Actually, like Ramsey, my advisor and I had the same issue. She wanted me to graduate. I said I wanted to do one more thing, and she gave me the advice that PhD is not the end of your career. You understand that, right? PhD is only the beginning of your career. So move on. You go to the industry. You learn new things, and that's kind of pushed me out and joined IBM. I joined the high performance computing group at IBM, where we were building BlueGeneL, BlueGeneQ, all the supercomputers. We were working on file systems, performance tools, and so on and so forth. But without going into the technical side of it, the main thing that I learned in that journey is that really you do your best deep technical work in the first 5, 6, 7, 9 years of your career. That is the time where your boss doesn't bother you. You will not get a lot of, you need to manage this person, that person, so on and so forth. You can sit down and do a lot of this kind of work. I really grew my circle of influence. I've probably gone to a conference every month or so. Lots of conferences available. Talked to a lot of people. I built a huge network of mentor community. This is the only community, unfortunately, that I did not actually get to meet. But I've been to supercomputing, the networking conferences, and so on and so forth. So my advice to young students here as you are graduating is that make your first few years really deeply technical and build a huge community. The community is going to help you. You are going to help the community as well. So it works both ways. Second part of my journey, I basically did a good job at building HPC systems and so on. And when you do a good job at IBM, usually they will ask you, go work on something that actually makes money. Obviously, HPC is not one that makes a lot of money. So I started to actually completely throw everything I did in HPC and move into a new area, this thing called cloud. And this was in 2013, just for time reference. So it's very early days of cloud. Nobody knows. People are making fun of cloud. People are taking seriously what cloud is doing, Amazon is doing, and so on. And that's the time. And in fact, if you are in HPC, everything is about performance. If you go to cloud, it's actually everything is not about performance. It's about usability. It's about consumability. It's about elasticity, everything else. But performance is kind of the last thing. And so I'm able to kind of basically throw away, get into a new field, learn things there, and started to build a lot of different cloud services. But really, my HPC background came into use there as well. So don't be afraid to take new challenges. They are going to come. If there is anything that's constant, that's really changed. My mentor, Jim Brown from UT Austin, passed away as well, told me, that's the only thing that's constant is change. So adapt to it. And I think change is going to be even more rapid in the next many years. In the last 5 years or so, we actually embarked on this journey of AI. As many of you know, IBM has been doing AI for a long time. We have won the Jeopardy and so on. But then we started to reinvigorate all of our AI efforts around 2021 to capture this new AI buzz. So we built AI systems in the last 4 years. That's going to be the rest of my talk. But the biggest thing we have done in building these systems is, if you are in kind of industry, one way to build AI systems is actually build them exactly like HPC systems. You just deploy them like a traditional bare metal InfiniBand. NVIDIA will, if you have deep pockets, NVIDIA will sell you actually a shrimp rack system that you can just buy, deploy, and run. That's one way to do it. That's surely a successful way, but a very expensive way. It brings you a lot of constraints. The other way to say is, OK, what are the AI workloads? What are the characteristics? How do I actually re-architect the entire system? And that's what I've done in the last 4 years. So my message here is, really, I felt like I actually was perfectly fitted for this role because I had the background of HPC, I had the background of cloud. And so we went and did AI systems in cloud, like HPC systems, but bring all the cloud characteristics. The final thing I do, and I encourage everybody to do it, and I think we should give a round of applause to all the mentors that took up the role here. If you don't mind, this is a great job. I benefited a lot from mentoring. I actually continue to benefit a lot from mentoring. I have a number of mentors. Every conference I go, I spend maybe 2-3 hours actually with each of these people, tell them my issues. Sometimes my mentors tell me what their issues are, which is OK. And then we kind of brainstorm on ideas and so on. And this becomes kind of a lifelong friendship that continues. So I do that quite a bit. I also teach. I used to teach at NYU. Now I teach a course once every year at Columbia University on cloud and machine learning. It's really exciting to interacting with students and help my kids. I have kids as well, and their friends on various kinds of Lego challenges and things like that. So do help. It's actually a lot more fulfilling. Otherwise, your work will consume you. So this is one way to de-stress yourself actually out of all the day-to-day work. So with that, I'm going to get into the main part of my talk. So what's new in AI? Of course, all of you, I'm sure, know what is new in AI. It's ChatGPT, it's DeepSeek, that's all in your minds. But let me take a little bit of a step back. So how did we get here, right? So if you look at the history of AI, starting in 2021, this is a trend that we have actually noticed, and others as folks at Stanford, for example, noticed as well, which is where previously, we are building AI models by taking data that you need to label a bunch of data, then you curate it, then you build an AI model, then you fine-tune it for a particular use case. And you keep doing this, and we have done a bunch of these models actually in our own labs, which is a very non-scalable way to actually bring AI to masses. And this is one of the reasons why, although we had great success in winning a Jeopardy championship, that did not translate in all reality to a lot of the business value, right? And the big thing that changed is this concept of foundation models, where you don't no longer have to actually build a model for a different use case, but you could take a lot of the data. The data itself, especially text data, has a lot of information that you can use to train models because when you speak words, they are actually connected together, and so you can train a model using that information. And you build this foundation model. Once you have a base foundation model, you can then fine-tune it to do various use cases. And the way I explain to my students is think of foundation model as actually sending a kid to school for 12 or 16 years. So this is like the base knowledge. Everybody gets the same base knowledge. We all have that going through our own schooling. And once you are done with it, now is when you specialize. Either it's with RLHF, reinforcement learning with human feedback for a particular domain, coding, or solving puzzles, or doing some scientific activities. You can then fine-tune these models to make them far more usable, right? But this doesn't come for free. This kind of training a foundation model and then actually fine-tuning it to the different use cases is expensive. So the thing I wanted to cover here is usually this training part is what gets actually most of the attention, most of the press. There's a DeepSeek train a model for only $5 million. That really is like, I ran only a marathon and I ran only 26 miles. Not telling you how many hundreds of miles you run before, and not telling you all of the cost that went into it, right? So what I wanted to do was actually I wanted to cover the whole landscape of the activities that go into actually training these models. So before we go there, let me just tell you a few use cases, because I think it's always better to ground your thinking in a particular use case. So for us, at least in IBM, the use cases centers around three important domains. One, of course, we are the IT and support for large organizations. What do our large organizations do? They do actually coding. They build applications. They build use cases. They build workloads. So one of the key use cases for us is coding assistance. There are thousands of developers within IBM, and all of the corporations that we deal with have thousands as well. And so one of the key use cases is actually helping coding automate, right? Generating hints, generating coding semantics of fix bugs, help with debugging, things of that nature. That's a key use case that's actually gaining a lot of traction. The second one is customer service assistant. So these are chatbots. These are when you make a call to your wireless provider why something is not working, helping you to debug kind of things. These customer service assistants exploded during COVID time as people have actually stayed at home and had all kinds of issues. And this continues to be a huge area for not only us, for many other organizations. And the final one, which you don't see as much kind of from saying outside, but actually in the internal organizations, workflow orchestration is a huge deal, right? So when you go to Amazon and click, select an item and click buy, there is actually a huge amount of workflow that happens in the background that results in somebody picking the item from the bin that's actually somewhere and putting it in the cart and then shipping it to your place. And the same thing happens with IBM, for example, when I'm sure you have all made reservations to get here. Huge number of those reservation transactions actually run on IBM systems. So there is a huge amount of workflow orchestration that happens behind the scenes to deliver goods and services to end users. So these are all kind of just a glimpse of the different use cases that we are targeting with these kinds of enterprise AI models. And the way we target them is this a collection of AI models that we ourselves train. They are called a Granite series. So Granite for code. This is a Granite AI model, a foundation model that's trained, but then fine-tuned for code. It's trained for 116 different languages, including COBOL and Fortran and so on and so forth. There is various configurations of these models. There is a 3 billion model, 8 billion model, 20 billion, and so on. These billion models is the size of the model. Think of it as a parameters in the AI model. And we open source these models as well. So for people that want to actually understand what these models are trained with, there is an open source repository where you can find information about those models, as well as there is a paper associated with it that actually tells you what data sources are used to train the model. So you can go validate it. So we kind of put all of that out. For the languages, we further train these granite models with various language information. I think we have one now with 8 different languages, Japanese including, multilingual and so on. And we focus more on the smaller size of the models, but with a higher quality data, because the model size has an implication on the inference cost, which we'll touch in a second. And the final one is, I'll just briefly mention, there is a lot of industrial use cases of time series data, either it's your refrigerator or your air conditioning system and so on and so forth. They all produce constant time series information, and we find a lot of use cases in the time series data. So there is a Granite time series models as well. So all of these models had to be trained, and so this is the infrastructure that we have built to support training, inference, and tuning of these models. So let me just show you the overall workflow that I promised a second ago on this infrastructure. So AI model training, typically we talk about training, but actually it starts at data preparation. And this is a process that's labor intensive, that computationally intensive, and that's actually more data intensive. Data preparation is where you it's almost like digging for gold in dirt. The data is everywhere. There is a huge amount of data that's out there, but not everything in that data is actually valuable or helpful. So our data preparation typically starts around 10, 20, 30 petabytes of raw data, and then you filter that data out to get eventually maybe 1 trillion, 2 trillion, 10 trillion kind of tokens. So it's a huge funneling process. And each time you are doing data preparation filtering, you are trying to look for certain patterns. If you are training a model and that goes in an enterprise, you want to make sure you don't have hate and abuse kind of text. But at the same time, you don't want to miss the nuances of communication, right? So how do you do that? Those are the kinds of processing steps that happen. It's a huge data exercise, as I mentioned. Most of this data typically starts in a object store kind of configuration, and then you read the data, process that data, and then you store it back into object store. So a lot of the computation for this kind of jobs takes hours to days. There is usually every team that's training these large models have hundreds of engineers that are data engineers that are actually just working on this process. Thousands of cores of compute is needed, and this process is repetitive. You don't do data preparation once and you're done. Actually, you have to go train a model, look at it, and then you go keep repeating this process. Not a huge amount of GPUs get used, and there are some steps where GPUs are used, but there is always hundreds and thousands of steps involved in this job. So that's data preparation for you. In AI, that's one really computation and storage demanding application. The second one is distributed training. So this is where once you have the data and there is a process where your engineers look at various configurations for the AI models. They go through, it's like preparing for the marathon. So they train a smaller model, run few miles first day, a few miles next day. You train a smaller model, you look at the hyperparameters, you train another slightly bigger model, and you get the whole thing ready. And then you launch your distributed training job. Approximately, the preparation takes about the same amount of infrastructure as actually training the model. Sometimes training the model is actually less time than the preparation. Like in the case of a marathon, you'll run far more miles than actually just doing the marathon. This takes weeks to months. And so when you look at DeepSeek, actually the number that they produced was $5.5 million and some number of GPU hours. What they said was exactly that particular model training. You only do the exact training that they have done, but not all of the preparation. But typically, this is significantly expensive in compute cycles, and you throw hundreds of thousands of GPUs at this problem, hundreds to thousands of GPUs. The next step is once you have the model, again, the end of the distributed training is not a model that you will directly use as is. It's like, at the end of your high school is not when you're going to workforce and start to work. There is fine-tuning that happens, right? So that's where the model adaptation and fine-tuning process starts. Typically, this tends to be hundreds of jobs. You fine-tune in many different ways. Sometimes you fine-tune halfway, and then you actually go back and re-fine-tune the process. And this fine-tuning doesn't have to be a job like a distributed training job. It could be running on a subsets of GPUs. You could parallelize the fine-tuning operations. You might actually fine-tune exactly the same process through multiple different paths, and then evaluate and pick the best one, and so on and so forth. But once the fine-tuning happens, this is when you actually deploy this model into inference. This is where end users get to actually access the model that you have trained and pre-processed and fine-tuned. Frankly speaking, nobody makes a dime in the first 3 steps. First 3 steps are completely cost, of course, except NVIDIA. They make a lot of money selling GPUs, but the rest of the people don't, right? The place where it has true value to a consumer is at the inference time. And inference, as you can imagine, is a highly demanding, interactive process, especially with the newer models where you have chain of thought reasoning, where the model is actually reasoning on what you are exactly asking and doing a lot of computation, and it eventually spits out an answer. This is a very computationally intensive task, as well as a memory intensive task. So most AI model performance is actually dictated by the memory bandwidth of the GPUs. And of course, you expect once ChatGPT or DeepSeek or IBM, once we put out a model, you expect that model to be available 24/7, and you expect it to be performant and producing response times within a reasonable amount of time. So it's a web application with a huge demand on horizontal scalability and responsiveness. The main metric that is used from the inference side is usually dollars or dollars per million tokens. That's a metric that gets used, and that's actually how most of the people get charged in many of these AI services. So that means optimizing cost. Today, everybody is exposing these models at any cost, basically, to gain market traction. But the place where if AI were to explode and get used in the long run, that cost has to be really optimized. Right? So I wanted to, when I give these talks, I kind of try to give some kind of intuition for people. So when we talk about distributed training, what do we really mean? And where did we start and where we are right now? 2 main things I want you to remember is data and the model size. So this is, I'm going back a little bit in, when we started the whole work on our AI system, this is in 2020. And we have done a lot of user surveys to figure out what will be the data size. And the biggest data sizes that they could tell us about 100 billion to 200 billion parameter tokens in data size is kind of what they were envisioning. Of course, now it's 2020 and vision is 2020. We can look back and we know this data has exploded. So what I'm showing on the right-hand side is all the way up to 2024. On the vertical axis is the billions of tokens. In fact, this graph I made in March of 2024. Now it is 10 trillion to 15 trillion tokens is what the commonly accepted data set size. So the bar on the right is actually much higher, is another factor of 2 larger than what it shows here. So the amount of data that we are throwing at these AI models is just exploding, is going exponentially. That's just data. So that's one factor that goes into training these models. The second factor that goes into training these models is how big a model you want to train. And in 2020, 21, if you ask even the top research, they would say maybe 1 billion parameters is kind of the place where we would train. Nothing bigger than that. That has gone to 10 billion, that has gone to 100 billion. Now we are talking close to 1 trillion. Actually, some of the models are 1.2, 1.4, 1.8 trillion parameters. DeepSeek is 670 billion parameters. Of course, there is a mixture of experts. I won't talk about that right now. But the size of these models is growing exponentially as well. It's not only just to train a model that end users consume. Nowadays, there is a lot of these models that are trained as teacher models. So you train a large model that becomes your teacher model. Then you go train much smaller models that are student models that will learn from these large teacher model. So when you are designing a system in 2020 or 2021, you would be expecting 1 billion, half a billion to 1 billion or 5 billion. but this is where we ended up being. So what kind of compute do you really need if you want to support these kinds of models? As I said, the two parameters are data and the number of parameters that you will use in your model. And the math is really, really simple. This is the dumbest math you could figure out. It's really just the multiplication of the amount of data and the number of parameters of your model. That's what dictates the amount of compute. In fact, the equation is, a sixth grader can remember this. It is for every single parameter and token combination, you perform 6 computations. So it's 6 times the number of parameters times the number of tokens that you have. That's the amount of compute you need to pre-train these models. I know my AI folks will say, 6 you are assuming activation checkpoint, 4 it is not. For this crowd, I don't think that's that relevant. But that's the kind of compute that you need for just pre-training your model. If you talk about just inference, just think of it as doing just forward pass. Forward pass is 2 computations for every single parameter and token combination. So it's 2 times n times d instead of 6 times n times d for inference. For fine tuning, you will use a small set of data, so your d will be smaller, but your n is still the same. So that's how you compute the amount of compute cycles you need for fine tuning. Okay, hope that's helpful. All right. Okay, so I just want to remind you, when we started this whole work designing these systems, we were in 2021, and we are trying to design what kind of a system we have to do. So we did our best to design our first system in 2022. That's what we call Vela Part 1. So this is a system we've designed in 21. We delivered in 2022. Our users were using it. It's lots of GPUs with 200 gigabit Ethernet. It's in a cloud data center in part of IBM Cloud. In 2023, by the time we delivered the system, it became very clear we actually need a bigger system. And so we ended up delivering a next system called Vela Part 2. Essentially take the existing system, almost 4 times improve its performance, and I'll go into the details on that in a second. By the time we are done with that system, we needed more capacity, so we ended up delivering Vela 2 in 2024, end of last year. And that has about 8x more network capacity, 2x more compute performance, and so on. In the meanwhile, if anybody is interested, these systems are not just limited to IBM Cloud. We actually package them and bring them to your data center. So if you have deep enough pockets, talk to me, and we can get one into your lab as well. So that's what we call Vela on-prem. A lot of the details on these systems are actually documented in an archive paper. In addition to building these systems, we also built an on-prem HPC system just to compare performance and usability and so on and so forth. So those are all documented in that archive paper. I'm also happy to let you know we have an ASP+ paper that's actually coming up in the next ASP+ conference, which has a very distilled version of the lessons learned from here. Okay. So what are some of our design principles is when we are thinking about these systems? Number one, of course, we are designing a cloud native AI system, but we wanted to make sure it actually delivers on performance. We cannot just say it's in a cloud, so it's very elastic and scalable, but it doesn't perform. That won't work, right? So performance is achieve state of our performance. But our clouds and many clouds are actually limited to Ethernet. Some of them do support InfiniBand, but vast majority of the fleet of infrastructure that's available in cloud is Ethernet. So we want to make sure we deploy these systems in Ethernet configuration while delivering the best possible performance. Second, as I just showed you, training the models, of course, a lot of the system builders start with actually needing infrastructure to train the models, but training the model is only one step. You really need to bring them to clients. So that's why it has to support the full life cycle of the workload. In parallel, we wanted to make sure it has all of the cloud flexibility, so operational agility and elasticity, so that we can grow and deploy the same copy of the system across our worldwide data centers. Not all of them are same size or shape. Some data centers, many cloud providers face the same thing. Some data centers tend to be really big, but in other locations where you have data centers in metropolitan areas and so on, they tend to be smaller. So you need to be able to deploy different configurations of these systems. And the last one, I'm sure you are hearing this as well. when it comes to AI infrastructure, the first thing that actually hits you is the lack of power and availability of power to feed these AI systems. So power, space, and cooling becomes a huge challenge, and we'll talk about this in a second. All right. So our Vela overall system architecture looks like this. It's a spine leaf configuration, a typical cloud configuration where there is n number of servers within a rack. Each of these servers is connected to multiple top-of-the-rack switches for high availability, and then those top-of-the-rack switches connect to multiple spine switches. So that means a packet that's going on a network interface has multiple paths to go. You could actually take any of these stores down, spines down, and so on. Still, the system will be operating. We expose all of the compute capacity through virtual machines, which is common in other cloud providers as well. What is different with us is we actually document all of this through open source Linux KVM QEMU, and we publish this information as well. So as I mentioned, our network cards are dual-ported network cards. Each port connects to a different Tor. There are multiple spines, and packets travel through multiple paths. We also use a tiered storage system. I'm sure this is of interest to many of you, where we have storage on the nodes. That's the local storage, but it's kind of treated as kind of non-persistent storage. Then you have persistent storage tier with a file system, and then there is object storage. And we'll talk about that in a second as well. This is just a brief overview of the compute node. Standard deployments of a lot of these compute nodes for training especially is a collection of GPUs within a node that are tightly connected with a high-performance networking. In this case, we have 8 GPUs that are connected with NVLink fabric, and those GPUs are driven by some number of CPUs, and then there is network cards that are attached to these GPUs that connect to the rest of the system. I'm going a little faster because I'm checking the time, and it looks like I have 20 minutes. So I'll try to wrap it up. What is our supercomputer part 1 is really this kind of a system where we are able to virtualize all of the compute capacity, but deliver bare metal kind of performance. We have spent a lot of time actually documenting this virtualization process, and we were able to deliver more than 90% GPU efficiency for the workloads in 2021. And remember, 2021 workloads are really, really small. So that's when 2022 came rolled in, and the requirement was we need at least 2x more compute, at least 4x more performance, so that we can train these bigger models that are required. And we have to do all of this in 6 months, and the previous system took us a year and a half. So that's the time where we went back to drawing board, actually celebrating after a couple of days, to figure out how to improve performance of workload by at least 2x on the previous system, but also double the capacity and improve the operations. One of the things that happens on these GPU nodes is they fail, and we'll talk about that in a second. So 2 things we have done to improve the performance by 2x. As I mentioned, when we deployed initial Vela system, we used TCP network. TCP means whenever GPUs need to communicate to each other, especially across nodes, if they communicate within the node, there is something called NVLink fabric that's easy to, that's a high bandwidth performance. But once you have to communicate across nodes, the GPU has to copy the data back into the CPU, and the CPU will use TCP protocols to communicate this information. And that works perfectly fine for the 2021 models, but when you look at 22 and 23 models, that is not sufficient. So we enabled this technology called GPU Direct RDMA over IBM Cloud Networking, which basically lets GPUs communicate directly, even if they are across different nodes, without ever actually going back to the CPU. So that means you eliminate all the data copies and so on and so forth. So as a result of this, we were able to improve the network throughput by 2 to 4x, and network latency by 6 to 10x, and train even a 20 billion parameter model in a reasonable time. So let me just show some data. I know a lot of you love the data. So the TCP performance would be something like the red line as a function of the array size. So as the bigger data, you saturate the network. When you are on the small end of the data side, you are more on the latency bound. But once you get to RDMA, or especially RDMA with GPUs directly, you get that green curve, which is almost 4 or 5x better performance than TCP, right? And we have done evaluations on how does this scale, right? So you might work with 32, 64, 128 GPUs, but does it scale to hundreds, thousands of GPUs? And I'm showing some of that here as well. But what does it mean for a workload perspective? Because when you're at the end of the day, you need to be able to train these models. And what I'm showing here is the red line is where the previous system 1x with the TCP networking, anything above that is better performance. And so we see a geometric mean of about 2x better runtime performance. So that means you can train the models 2x faster. So you reduce the time by 2x. That's just improving the existing system. I will skip this in the interest of time. The other one I mentioned is power, space, and cooling efficiency. Our initial system deployment, and actually this is an industry standard you will see in a lot of the GPU configurations. Usually you deploy either 2 nodes or 3 nodes in a GPU rack. These GPUs consume a lot of power. The A100 GPU, 8 GPU configuration consume 6 kilowatts. H100s consume actually about 9 kilowatts. And industry standard racks are about 20 kilowatts. So you deploy 2 nodes or 3 nodes of this, and then you're at the top end for the rack. One of the things cloud providers do is we actually provide rack with full redundancy. So that is, each rack has actually 40 kilowatts of power, but you are only allowed to use 20 kilowatts. In case of a PDU or a PSU failure, the other one can take over. That's always standby. That's always available. What we said is for HPC or for AI, maybe this model doesn't work. We should actually go revisit that and say, we always use the 40 kilowatts. We make the nodes throttle down if there is ever a power failure, rather than always have it available as a standby. So we double the density of the racks, but this means we need to have a technology that actually throttles the GPUs. So we worked with our vendors to make sure we can throttle this. So in this graphic I'm showing, basically there is 3 phases, phase AB, BC, and AC. One of the phases at the bottom, feed is stopped. So that means now if we run the GPUs at the same power, we blow out the other PDU, the GPUs automatically throttle down because there is a firmware that basically says not enough power, you should throttle down and you should run at a lower frequency. And so that throttling happens within about 1.5 seconds. Usually the PDUs from the industry are rated around 5 seconds, so they can handle a surge up to 5 seconds, but after that they will blow out. So what we have done is basically that kind of an optimization where we actively power throttle whenever we see power issues, but run at full speed if we don't see any issues. And this is a technology that we are deploying in the next generation server. We have deployed actually in the next generation servers as well. In fact, just on January 14th, we got a ping that said 8 of these PSUs have an issue. We need to go fix them. We pinged the user. I said, your job is going to throttle down. The user said, I don't see anything for 2 minutes, and then said, oh, yes, I do. And the GPU, which was running around 700 watts, throttles down to 150 watts. This is a much better design where the workload might run a little slower for a small, short period of time, and then it actually goes back up when things are fixed, rather than you crash the job and then force the user to restart it or actually take the nodes out. So this way we are able to bring both the cloud characteristics of elasticity and also consumability characteristics for the end users. The other one I mentioned is GPUs fail, and actually I wanted to use this slide to describe this. There is different types of failure that happens in GPUs, GPU nodes. Now, I classify them broadly into 3. The first one is very clear hardware failure. So you have a GPU failure, or a board failure, or a node failure. I call them actually good failures, and some people laugh at me. They are good failures because they are like, if you have a broken arm and it's actually bending down, you know it's broken. You can go to the doctor, get it fixed. But the other failures are like pain. You have a pain, you don't know where the pain is. Now you need to go through a whole diagnosis process to figure out exactly what the problem is. So the second set of problems that I have on the table, they're all soft issues where sometimes GPU running at a slower clock frequency, or memory cells are corrupted, and so your application is actually getting garbage information. Or your PCI link has degraded, so your application is running 10% slower than you expect, but you are just using 1,000 GPUs and 400 PCI links. You don't know exactly which one of these PCI links is actually causing this. So you you need to diagnose it before you can actually relaunch the job so that you can continue with the better performance. And so these tend to be a lot more difficult to diagnose. And so for this, we have been working on a tool called Autopilot. I call this the Apple Watch for GPU systems. It's always sitting there, it's monitoring stuff, and if you ever fall down, it will call the doctor, kind of thing, right? So we have this Autopilot that does actually 4 things. There is a mechanism by which it does a continuous checks. So if it notices that a GPU node doesn't have anything running, it actually goes and runs very intense tests periodically and see if the GPUs are still healthy or not. If it notices anything wrong, it automatically marks that node as evict. So the scheduler on the top will say, I will never place a workload on this, and it will actually inform the sysadmin to take a look at it. In the case where there's stuff running, it is constantly checking metrics coming out of it, logs and metrics. So is there something I'm seeing here? Are there abnormal messages, things like that? We also do pre-flight checks. So this is, before you take off any airplane, you actually go check. So a lot of these training jobs run for 20 days, 30 days, 40 days. So before you launch a long training job, you could request, I want a pre-flight check. So that means all the GPUs that are allocated to your job, we will go check them with a specific set of workloads to figure out if there is anything abnormal or they're all healthy. We do in-flight checks. So this is where we run non-intrusive kind of experiments to see if the PCI links or something else is actually causing any degradation. And for sysadmins, we also have something called on-demand checks, where they can say, OK, an end user reports my job is running 5% slower, what's going on? They could actually just go initiate a collection of checks. And this is all integrated into our scheduler. This is an open source project. Autopilot is an open source project, and I encourage people to come help us. We work with SUNY. I see a res here. We work with the Boston University. There are students actually working on this. We don't have all the GPU configurations. We don't have all even, in fact, my one wish to this community is we need an autopilot for storage systems, because right now my admins actually spend more time debugging issues on storage, and Vasily has been an excellent partner in that effort. But we need an autopilot for storage systems, and I think that that's a call for community to help. And this is an open source project, and these slides will be available, so you'll be able to click on them. I also have URLs in the references. All right. So let me just spend the last 10 minutes or so on the data architecture. And I'll provide a point of view. We do a lot of this training in the cloud. So I see really 3 data stories, right? So the first one is the object store. This is honestly the place where all of the AI data is actually going. This is where the data starts. This is where it actually ends up being. We deal with petabytes of this data in object store that goes into our clouds, as well as we hear the same thing in other cloud providers. The second one is distributed file system. Historically, if you look at a lot of traditional HPC data centers, distributed file system is the place where the data actually lives, both for computation as well as even for long-term residency. And of course, you have tape and so on. I'm just ignoring that for now. And then local storage. A lot of these GPU nodes have local storage. And in fact, the AI researchers would do anything possible to make sure storage is never their problem. So they will beg sysadmins, copy the data into my local disk and mark that node for me for the next 10 days. So nobody else uses it, I will just use it from there. Local storage is by far the fastest storage, of course, that's the place. But you don't have enough of it, right? That's problem number 1. Problem number 2, once you copy something into local storage, now you have actually made that node not usable by anybody else. Now you have to make sure that user actually uses it very productively. So you don't get very high utilization of infrastructure if you keep carving out dedicated local storage. The object storage clearly is the place where a lot of the data goes for most of this AI training. It provides the cost and the scale, not necessarily performance, cost and scale, but sufficient enough performance for some of the use cases. Distributed file system, at least from an AI systems perspective, the way we see it is really the cache for hot data. And this is where when you are computing, when you are doing training, when you are doing fine-tuning, this is where the data has to come from, because that's the one that provides the right kind of performance, bandwidth, latency characteristics that are necessary so that you don't keep these GPU nodes idle. But the key requirement there is this cannot be the place where people manually copy data from object store. This has to be automatically synchronized. We do have from storage scale, we have something called active files manager, AFM, that moves data back and forth, but there is, I think, a lot more that can be done so it becomes more seamless. There is a huge amount of input data that gets created. There is a huge amount of checkpoint data and intermediate data that actually also goes into this distributed file system. And the final one is really local storage. This is increasingly more and more of the computation cycles are actually going into fine-tuning and inference. And of course, if the AI journey was to be really successful in the next 10 years, we have to spend more cycles in the inference, because that's where actually the real value gets created. And there is a lot more data that's being created. There is cache for frequently changing data, the KV caches and so on. And interestingly, the FAST this year has 10 papers on AI. The previous year, there were 3 papers, and the previous year, there were 2 or something like that. So there seems to be an exponential curve in the FAST itself. And several of those papers are actually about KV cache, some variation of KV cache. Cache management for the model state. As I just mentioned, these models are becoming gigabytes and terabytes, and that model state has to be managed efficiently. GPU direct storage, while there is support for GPU direct storage in things like spectrum scale, I think this has to become more prominent. And at the end of the day, asynchronous updates back to cause. So my ask from a research questions perspective, really make data migration, data migration between these layers really as transparent to users. Right now, it is not. Users actually have all kinds of ways of copying data, or sysadmins copying data into these different layers, managing them, tiering them, and so on. And that data management also has to be such that it doesn't interfere with the jobs. I think there is intelligent ways of actually figuring out when network is being used by the application versus when it is free, and actually doing replication during those times. The other thing that I keep bugging Vesely and team is actually the DFS layer, the distributed file system layer in the middle, is not really elastic. It should become elastic. So I don't want to think about how big a caching layer do I need, rather than it grows and shrinks as the needs of the users change. Initially, we used to use cloud object storage as our source of truth for writing our checkpoints and so on, and an NFS file system for reading the input data sets. That clearly did not perform good enough, and that's actually when we went ahead and deployed our system with IBM Spectrum Scale, Storage Scale, or GPFS for those that are here. And that really helped solve 2 problems. One, these AI jobs, when they every time there is a failure or a restart of for some reason or the other, when the hyperparameters change, their data loaders actually load a lot of data, and that data loading time can be quite expensive if you are using a non-performant file system. So that's one problem that Scale has solved for her. The second one is, as you are accessing this data, you could also have a lot of variability in your execution time, because every time you are going to the storage, it doesn't give you the right performance. So you have a lot more predictable job execution time by using Spectrum Scale. But just giving you as an example. We are working towards, of course, this kind of arrangement of using high-performance file system as a cache has overhead. People have to manage it, and you need write tooling. We need an autopilot for the operations and so on. So we are working on actually making this as a service. Storage Scale as a service is a project Vesely and team are driving, where we have a number of use cases where this becomes really critical. With that said, so what are we running right now on Vela? This is the slide before I wrap up. We are running a huge amount of training jobs. We are also doing a lot of fine-tuning jobs, and all of our USENIX services are running on this system as well, on the worldwide data centers. So with that said, I won't rehash all of the technical details, but I wanted to kind of give a more higher level lessons insights. One, AI workloads change rapidly. And so if you are talking to AI researchers trying to build systems or trying to come up with new research projects, my advice is believe them only half the time or less than half the time, because they themselves don't know, honestly, right? The other way I think about this as I start to think about designing these systems is I'm going to assume that this is going to be massively successful. So if this is going to be massively successful, 100x better than where we are today, what should that design look? What will be the problems at that scale? I think starting from there and working backwards, I'm not saying you should always design it for over-design the whole system. But if you are not even convinced it's going to be massively successful, maybe you shouldn't work on it, actually, right? So if you think it's going to be massive, then you will actually start to think about this kind of issues that are not there yet, but that will come down soon, right? The other thing I learned really is you can spend a lot of time perfecting something, but actually you will learn a lot more by just putting it in the hands of people to use it, and then get feedback, and then keep iterating it. Of course, you shouldn't put it too early. Otherwise, they'll try it once, and they'll say, this is not working, and don't want to deal with it. Next, automation. As I just mentioned, I think we need to do a better job at actually automating a lot of operational issues. That's how we can make progress. Otherwise, when you put something in users' hands and they keep having issues, you'll spend more time debugging problems than actually making fundamental improvements. This is just starting, in my opinion. The whole AI thing is just starting, so be part of the journey. Talk to people here. I think there is a huge amount of opportunity here. I must say this is the work of a huge number of people. There are 150 plus number of people. A number of our papers have authors in the range of 200 people. While I'm speaking here, I want to thank all of these people that have contributed to this and many more. Finally, I have a bunch of references that will be available, but I'll just leave my slides here, and I'm here to answer any questions. I hope everybody is still awake, and I hope that was interesting. I really appreciate your time. Thank you.